There. Okay, we are recording. Put it up on that one. So, is everyone ready to present?
Yes.
Yes.
Good. Okay. Hello, everybody. Today we are going to present our work on the binding problem with a later focus on the multi-object network. We who are presenting today is me, Oscar. We have Harry, Wilmer, and Matthias. So, that's wrong. We as humans learn from an early age how to perceive what we see and divide up the received information into meaningful representations. For examples, a person could see that this bowl has red apples in the front of it and green apples in the back of the bowl. Or another example, if we took out the red apples, covered them with a cloth, and then asked the questions of what colors of apples are on the table, we would still be able to accurately tell that there is red and green apples on the table, because we can retain the information. These types of problems is what the binding problem describes, of how neural networks lack the capability to bind information between objects in a dynamic and flexible way. This can come in the form of keeping information about entities when the number of entities in a certain frame grows, both by keeping the individual information about each entity and the relationships between them. This could get muddied up. Or, for example, with the cloth, it can lack the proper capabilities of retaining information through time when the environment changes. Yes. And to address these problems, or to address the binding problem and getting neural networks closer to a human level of generalization, the paper suggests a possible solution to this problem could be addressed by tackling the three following areas. And those are representation, segregation, and composition. And these topics will now be addressed by Wilmer and Harry.
Yes. So one important feature of the binding problem, as Oscar said, is the problem with representation. One can view our world consisting of multiple building blocks, such as physical objects, sounds, colors, and even more abstract concepts such as behaviors and goals. Representing these building blocks in machine learning in a way such that they are modular and independent has been proven to be very difficult. Poor representation of building blocks can lead to things like the superposition catastrophe, which we can see here, where a neural network has tried to identify both objects and colors at the same time, leading to confusion whether it has classified a green apple and a red pear or vice versa. The paper suggests good representation should act as an independent degree of freedom in the feature space, so that new independent representations can be built from existing ones, and that different building blocks do not interfere with each other. The paper also suggests that all representations also need to be presented in a common format in order for the representations to be effective. Representations also change over time, so the representations should be updated according with time, and their history should also be represented as an individual building block.
So some of the solution to these representation problems is so the model can store the separate values without interference is one vector symbolic architectures. These are algebraic operations like convolution or tensor product, which bind features together in a clean, reversible way. Another approach is capsule networks, which represent objects explicitly using groups of neurons, along with a pose information like orientation and position. The main benefit of these representation methods is that they create a cleaner, more disentangled internal structure.
So if representation is what we know about objects, then machine learning methods need a way of knowing how to create these representations as well. That is, how can a machine learning model take raw sensory input and distinguish or extract representations? This is the next important part of the binding problem, according to the paper. With bad segregation, all representations of objects will become entangled and seen as one singular mass. The paper suggests that machine learning models have to understand the hierarchical structure of objects, that most objects consist of multiple other objects, etc. Objects also consist in multiple domains and have to be distinguished accordingly from each domain, so that some objects can be identified through sound as well as visual input and things like that. In the real world, multiple objects consist together in a scene. Machine learning models struggle how to decompose multiple objects into representations of singular objects and combination of them simultaneously. Because for different tasks, different compositions of multiple objects prove to be more useful than others. For example, as we can see in the image here, we have multiple shares grouped together. They can be seen as one entity, but for some tasks, maybe if we want to move all the shares, it might be more useful to see the groups of shares as singular objects in contrast to single shares grouped together.
One popular approach to solve segregation is slot attention, which literally groups pixels of features into a set of object slots. This gives the model a clear representation of each object. There are also probabilistic models like MONet, which we're going to talk more about later, and I-9, which learn to decompose scenes into objects through generative modeling. Another technique is spatial attention, where the model selectively focuses on different regions of the image. Segregation is important because it prevents different objects from interfering with each other. So now I'm going to talk about the last problem on the binding problem. Composition is the ability to understand a situation by combining multiple smaller parts. This is something we humans do very naturally. For example, we can easily understand phrases like bigger than, taller than, or Mary hit John. All of these depend on multiple elements and on how these elements relate to each other. For artificial intelligence, composition is extremely important because it enables different forms of reasoning. A simple example is spatial reasoning, like A is left of B. Another example is relational reasoning, where we build relational frames. If the model knows that A is smaller than B and B is smaller than C, it should also be able to generalize that A is smaller than C, even if it's never seen this combination before. So overall, composition is what allows model to combine known elements in a new way, which is crucial for generalization. However, composition is very difficult for neural networks. There are two big reasons I highlight here. The first is inferring structure. For a model to compose elements correctly, it first needs to understand what meaningful parts of the inputs actually are. For example, take the sentence, time flies like an arrow and fruit flies like a banana. The exact same words appear, but the structure is completely different. Humans immediately infer this structure, but the model has to discover which parts belong together and what roles they play. Mistakes in this inferred structure break the entire composition. The difficulty is the lack of explicit structure in neural network. The second difficulty is the lack of explicit structure in neural network. A classical neural network don't naturally build symbolic relations. Everything is represented by vectors, all mixed together in the same space. This makes it hard for the model to tell objects apart and know how they relate. The consequence is poor generalization. The model struggles to handle new combination of elements even if it has seen the parts before. So these two challenges, inferring the right structure and lacking explicit relational structure, make composition a hard problem. Yes. So the solution of composition, where we want to build structural relationship between objects, has multiple approaches. The first one I talk about is relational networks, which explicitly compute pairwise relationship between objects. They take as an input a set of object vectors and learn how those relate. And there are also graph neural networks, GNNs, which takes further representations as nodes and relationships as edges. This provides a structured, flexible way to do interaction. There are also graph convolutional neural networks, which build in a similar way, but on images, which can be used for reasoning and question answering. And also neural computers, who goes even further towards symbolic reasoning. They can store, receive, and manipulate information in ways that resemble variables in memory in classical computer. This allows them to perform structure operations and roles, almost like running a program. All of these methods help neural computers build relationships, enabling reasoning and systematic generalization, which are the core goals of composition. You can take it, Matthias, with the MONet.
So we decided to look at this article, MONet, Unsupervised Scene Decomposition and Representation, which is about computer vision and object-centric learning. And why do we need this? Well, it's because humans perceive the worlds in terms of objects, and whereas deep neural networks process pixels. And many models struggle with occlusion, generalization, and compositional reasoning. But the multi-object network, MONet, suggests a generative and unsupervised method that decomposes the scene into meaningful components. So the key takeaway is that instead of learning a single scene representation, MONet learns representations for each object. We can go on to the next. And this is the core of the architecture, where we have a recurrent attention network and a component variational autoencoder, the VAE. Next. Where the first part will iteratively generate an attention mask, and each mask will isolate an entity in the scene. And the scope ensures that pixels are explained away step by step. It's sort of saying to the next step, dear VAE, for slot K, please pay attention to these pixels. They likely belong to one entity, and you should ignore the rest for this step. Next. And component VAE then will process these masks. Each masked region is processed by one shared VAE. It learns a latent representation for each object and reconstructs its portion of the scene. And then the final scene reconstruction is the weighted sum of component reconstructions. Next. And these slides shows what the network does. It takes the input image, and you also see the reconstruction mixture which is what the MONet generates by combining all the individual component reconstructions. And the segmentation row is where each color is one slot's mask. It's what that slot focused at. And here you also see the unmasked versus masked versions of the output. So the unmasked is what the VAE thinks the object looks like, and you see it covers the whole scene. And the masked part is filtering with the learned mask from the VAE, and it shows what the part of the object is placed back into the scene during full scene reconstruction. And this model actually it generalizes outside of the training regime and the data distribution. It handles empty scenes, different number of objects, and identical colors. Next. And it also handles occlusions by inpainting and segmenting overlapping objects, as you can see in slot 4, indicated by the cube and the blue ball that the red arrow points at. It is occluded by objects, but the MONet understands that it should be a ball behind there. Next. So how does this network relate to the binding problem? Looking at representation, it uses object slots where each slot produces a separate latent vector representing one entity in the scene. All slots use the same VAE, enforcing a shared and comparable feature space across objects. And the latent representations disentangle object properties like color, shape, and position. And occlusion inpainting shows that the MONet maintains a stable internal representation of objects, even when the parts are not visible. And segregation. The recurrent attention mask assigns pixels to different slots, grouping pixels into components. And the explain away dynamics ensures that each slot focuses on unexplained regions, forcing the masks to partition the whole image into distinct components. But it does not tackle composition. It simply stops at object discovery. You can move on to the next. It's about object discovery and representation. Next. And these are some of the limitations of the network. It's only using synthetic datasets, no natural images, and there is no temporal or relational understanding. And it also requires a fixed number of slots. The strengths are that it is a fully unsupervised segmentation. It handles occlusion, generalizes to different number and set of objects, and it uses a shared latent structure across entities. Next. I think this is a duplicate, maybe.
Okay. Okay, thank you, Matthias. So our conclusion, we're basing this off the paper where it mentioned it is in its conclusion the vital importance of having a dynamic and hierarchical segregation process, and how this segregation must be done in an unsupervised fashion for it to be able to handle real world environments where the ground truth cannot be found. So we think that the MONet raises a worthy candidate for continued work here, as it is unsupervised in its form, and for its way of handling segregation and representation well in its paper. But for continued work with the MONet, a vaster selection of data sets would have to be tested on the model, and maybe some adjustments to see how it would handle real-world environments of more complex structures. Yes, this is our short conclusion. We would like to thank you for your time. And this is the end of our presentation on the binding problem with the focus on the multi-object network. Thank you very much. Okay, so we stop the recording.